So this is kind of a place that we start in Dirac calculus, and that's talking about variables, constants, and parameters. So what do you think when you see this expression, 2x minus 7 equals 0? So when you see that, what comes to mind? What do you think?
Solve for x.
Solve for x. What were we saying, Veronica? Solve for x. And then what is x? 3.5. 7 halves, right? Is that what you think? Okay, so could x be 4 or 10 or negative 0.5?
Yes.
They're saying yes.
It could be wrong, but it could be.
Could be, but it's wrong. Doesn't x have to be 3.5?
Because it's like I guess the mystery number in this case, even though it has everything. But
Okay.
it would be wrong, but
So
answer.
tell me how x could be 4 or 10 or negative 0.5. Oh, but now you're saying if it doesn't equal to 0, so you are saying x does have to be 3.5. But you're arguing I have to change the equation. Could x be 4 and that equation still be there? Okay, so if you're saying no, then you're saying x has to be 3.5. So, okay. Does anyone think that x could be 4 or 10 at negative 0.5 along with that equation?
I mean, nothing says we're in
Okay. It would just, what would be wrong?
the
The equation would be wrong. So x wouldn't be wrong. The equation would be wrong. Okay, so what about this? Suppose that same x was the number of hours elapsed since your plane left the ground. And also 2x minus 7 equals 0. So could x be 4?
yes.
What would it mean
X would be
if x was 4?
4 hours since you're playing with the ground.
4 hours since your plane took off, right? And what about negative 0.5? Could x be negative 0.5?
It'd be 30 minutes before.
30 minutes before the plane took off, right? Okay. So then what is the 2x minus 7? Well, maybe that's a particular, so this is the idea that variables vary, right? Like you're going through your day when you were going to take your flight, and you get to the airport, and every moment x is taking on a value, and that's changing, right? When you're walking through the airport, when you're going through security, when you're at the gate, it's varying, right? Negative 15, negative 14, negative 11, negative 5, negative 1, 0. We're taking off now, right? 1, 2, 3, 3.5, 3.6, 3.7, right? So as you're doing this thing, going somewhere, in the background, x is varying, right? X is taking on all these values. And maybe 2x minus 7 is like, that's when the first time they gave you a drink or something like that. Like crummy flight, right? 3.5 hours in, you get your first drink, and then you have to pay like $10 for it, right? Okay. So we want to think of that variables vary, right? So there's a situation going on, and the value of x stands for something, and as it unfolds, that value of x can vary. Rather than 2x minus 7 equals 0, that means x is 3.5 and it's never anything else, right? So in this situation, x could be any real numbers. Okay, so x equals 3.5 simply highlights a particular moment on the flight. So what we mean by a variable is a letter notation that represents the value of a changing quantity. Okay, and then likewise, so a constant is any non-changing value. No, not in a given situation, no matter what. I don't know why that says that. Yeah, that's a parameter. So constant is not changing value no matter what. It shouldn't say in a given situation. It said it's always the same. Never changes. Okay? Okay? A parameter is a letter that represents a value of a constant that's constant in a given situation, but that might change if you change the situation. Okay? So in a given situation, variables vary. Parameters stay fixed until you change the situation, and constants never change. So what's an example of a constant? What's that? Pi, right? Pi is a letter that represents a number that never changes. Pi is always that same value. What's another constant? What's that? the acceleration of gravity, right? The acceleration 9.8 meters per second, right? Per second. So those are things that never change. Okay. So let's look at this. Let's just practice that. So here's the situation. Circular pond for raising fish has a depth of 5.4 feet, a radius of 28 feet. It was filled at a rate of 17.9 gallons per minute, and the volume of the cylinders pi r squared h. So each of these, I want you to talk to the person next to you and say whether each one is a variable, a parameter, a constant, or none of the above. Maybe it's none of the above. Remember that variables and parameters are letters. They're letters that take on either a changing quantity or a fixed quantity in the situation. All right, so for it to be a variable, a parameter has to be a letter. Okay, go. So partner up or talk at your table. None of the above. None of the above is a choice. Yeah, none of the above is a choice. At least one of those is none of the above. Should we talk about them? Okay. How about capital D, the capacity of the pond? They're saying parameter. We agree. Okay, cool. Pi. Constant. Okay, 5.4 feet, the depth of the pond.
Oh, it's neither because it's a number. You need a symbol.
Right. So if it were like D equals 5.4 feet, then D would be what? Parameter or variable? Parameter. But since it's just a 5.4 feet, it's just a non-changing quantity in the situation. It's not technically a parameter because it doesn't have a notation for it, right? A letter. Okay, R, the radius of the pond. We agree it's parameter? Cool. Number of fish in the pond. None of the above because?
It's not a letter.
Right, so if it was F equals the number of fish in the pond, then what would you say? Over time, it's variable, right? On this day, so you'd have to say, are we talking about this day? Probably a parameter, right? But yeah, over time, it would be a variable. Okay, what about H, height of the water in the pond? He wants variable, agree? Variable. V, little v? Variable. 32.17. Constant, right? It's a constant. 70.9 gallons per minute. Constant? Parameter? Constant?
It's not a letter.
But I still feel like it's a rate in this situation. That's
Okay, so if it's a rate in this situation, then what would it be? Parameter. That's not a letter.
oh,
Final conclusion? None of the above, right? So it's like a parameter. It's if it was like a capital R for rate, or G for gallons or something. If you assigned it a letter, it would be a parameter because it's basically they say fill at this constant rate. So it'd be a parameter if it were a letter, but it's not, so it's none of the above. Let's see if my answers agree here. Parameter constant. Okay, we said the same thing, right? Cool, so let's do a visual example of this. First, split the screen here. I got something to do. Which screen are you guys going to get? Okay, you get the blank one. So I'm going to give you this. Okay, so here's something we're going to work towards in the Dirac calculus, but we're going to use it for a different purpose today. So we'll be talking about what this means. We'll be talking about what this means later on. But for now, we're just going to use it to do a similar exercise to what we just did. And that is, we want to identify, you got 5 different symbols there. Okay? left of x, dx, and x. So for each one of those, I want you to, first of all, determine if it's a, and it should, once it gets through, it should speed up. It'll speed up and get smoother, it should. Whether each one of those is either a variable or a parameter, okay, either a variable or a parameter. And then if it's a variable, what's its domain? Meaning what values does it take on? Right, so if it's a variable, I want you to determine the domain, or its possible values. If a parameter, then what is its value, right? That's one value. A single value, what is its value? Is the task clear? You know what I'm asking you to do? Go through each one of those, determine if a variable or a parameter. So you're just looking on the x-axis, basically, around the x-axis. And then if it's variable, over what values does it vary? So what's its domain? And then if it's a parameter, what is its value? A, parameter or variable? People are saying parameter. Yeah, stays constant in this particular situation. What's its value, Lydia? 0.5. You guys agree? Easy one to start. Good. Delta x, variable or parameter? What'd you guys say over here? This Alyssa here. Yeah. What'd you guys say for delta x? Constant? Parameter, yeah. So it stays constant in the situation, and so therefore it has a particular value, which was 1.5, right? So it's showing it in different places, but the value itself is staying constant at 1.5. Very good. Okay. Left of x. What did you guys say? This, Alyssa.
We said left of x was a variable.
Variable. Why variable?
Because it is changing.
Right. So how is it different than? How is this variable different than maybe like the x when we talked about the plane, the time since your plane took off from the ground? How is this variable kind of has a different aspect to it? How?
Because it's not on a linear graph, and then this one, like your left of x isn't always going to be like.
Changes in intervals of 1.5.
Okay. Yeah. So this is the technical term is discrete versus continuous, right? Like the x value in the previous example with the plane was, as a plane flies by, right? As I said that, was a continuous variable, right? It takes on like every real number. When the left x, it takes on discrete values. So that's kind of the technical term for that. Like so, it's like taking on a value every 1.5, but still changing. So it's like a set of numbers that you could write down, right? If x is continuous, you could never do that, right? You could never write down all the numbers. Okay, cool. So what is is variable, and what's the domain? What's the domain? Which I was just talking about, right? So what's the domain here? Veronica, what's the domain for left of x? I'll go back and start it over. Right, that was part of your task. If it's a variable, what's the domain? So let's start it over here. You remember what I mean by domain? What is domain? Hey, it's safe here. No one's gonna. You can get it wrong. It's okay. So when I'm asking for the domain, that's where we got to start. What am I asking for when asking for the domain, Lydia? Right. So what would it be? Any value from 2 to 14. Agree with that? Winston, why not?
It has to be on the interval. It has to be in intervals of 1.5.
Okay, so tell me what the domain is. If you
It would be like 2, 3.5, 5,
So 2, 3.5, oops, 3.5.
5, 6.5, 8.
That's where I got confused. I wasn't sure if you were asking from where it started to where it like ended. That's why I got.
Yeah, so in this animation, so you could, yeah.
Okay.
So then ask, if you want to ask a clarifying question, you just ask, what to say. Do you mean in this animation, or, if you just give an answer with whatever you're thinking, that's fine. But, so, Lydia, you're right in a sense that you had like the range of them, like the starting and the ending, but it's really important that it's not just every value in between, right? It's only the ones that are every 1.5. Okay, cool. So how about dx? Somebody new. Jason, what's variable?
Well, df(x) would be a variable because depending on, I guess, what interval you're on,
Uh-huh.
and then since it doesn't complete like a full interval,
Okay.
then it varies between, I guess, the intervals of like that 1.5.
So what values does dx take on?
Yeah, couldn't it be all of them?
All real numbers? Dx takes on all real numbers? Agree with that? What do you think? 0 to 1.5. Takes on the value 0 to 1.5.
Oh, because it's just like what we're adding on to the other interval.
Well, it's kind of like the length of this arrow, right? Dx is showing us the length of this arrow. So when it's kind of like repeating, right? So when it starts, what is the value of dx? Now. Okay, and so now it's increasing. And then when it ends, 1.5. So its domain is all values 0 to 1.5. And that's a continuous variable, right? Okay, last one. X. Same thing, variable or, oh, I had a fancy question up here. I didn't use it. So slow. That's a lot of math lines in GC, right?
Yeah.
Well, it's because there's so many symbols, right? So what's going on? Why does it keep jumping up to the top? Me too. Is it down to, oh man.
Maybe just stop it.
Oh, I know why. Because that's where the cursor is on the first one. Yes, that is the key. But it shouldn't have to do that. It never had to do that before. It's this new version. Okay, now let's get the cursor down here. There we go. Okay. So what about x? X less 1. Variable. Okay. Domain. Any whole number. What do you think? Any whole number. Is that the domain? Any real number. So whole numbers are what? Like 1, 2, 3, 4. So is it jumping from one whole number to the next? No. It's taking on the values in between? Yeah. So x is kind of representing all real numbers, or on this animation, it's representing, what's the starting value of x there? 0?
Well, 0 to like infinity, I guess.
Well, so in this animation, though, here's 2.5, 2. Where's it end? 14. Okay. But so yeah, maybe we think all values greater than or equal to a. So maybe it could start at a, and just keep increasing. Another way to interpret the domain would say like x is greater than or equal to a. Okay, questions on this? So here's that payment formula, right, in GC. And then here's the function version of it, right? You explored doing method 3. Like last time in class, we looked at just putting the numbers in and getting the answers, creating a formula with parameters, changing the parameters, and watching the value of the formula update, right? And then for your homework, you looked at kind of method 3, which was using a function, right? Using function. So here's the payment formula, and here's a payment function. And so what's the difference?
One uses
What's the difference between a formula and a function? This is a really important question.
function notation, and it's just like the name of it.
Okay, so you're talking about the function has function notation. And where are you looking when you say that?
Like the left side of the equal.
The left side, he's saying this is different. And this is called function notation, right? Okay. So how does that make it different? The fact that it has function notation and this doesn't. This just has another parameter for the value of the formula, right? But these are identical, right? The right sides? Exactly the same. So it has to do something with the difference between having function notation and just a parameter which stands for the payment. So what's the difference? Yeah, Veronica.
You can change the values of the function notation line, but like when we set it with the parameter we gave it
Yeah.
specific value.
Yeah. So you're talking about changing these values.
Like when we wrote it in for like the assignment,
Uh-huh.
we just wrote it in like that order, like
Mhm.
in parentheses, and it just gave us the answer for plugging it in.
By putting numbers in there. So in one line, rather than in one line, you could just write the function notation with the numbers filled in, and then boom, it gives you the answer. What do you think? Is that convenient? In what situations would that be convenient? What did you say?
I said last night when I
Oh, on the homework. Okay, but can we think of like can we scale this out to other situations? Because really, actually, so it takes 3 more lines to define RP and N, but really you just type payment and you get that number versus just typing this with your numbers plugged in there and getting the number. So yeah, you save some lines, but what is the real advantage to that function notation versus PMT? Okay, cool. Yeah. So in that line where you write PMT and you just look at that line, do you know what your inputs are? Okay, but when you look at this, the function notation, right there in that line, you know. So if, say, I wanted R to be 0.0625 and P to be 175,000 and N to be 180, what would it take to represent this payment? I want to represent. I don't want to just write payment. I want to write something that shows me those values. What would I have to write to show me those values? That R was 0.0625, P was 175,000, and N was 180. What would I need to write to represent that with those values? In the formula case. Right, so I'd have to actually use the formula itself to represent a payment with those values. But what about the function notation? Yeah, do you see how, so if I do f of, what am I going to do? F of what? My order rate, RPN. I got to get the order right? Or else we have the exact same situation that we had in homework, right? So R, what did I say? P was? Okay, is it working here? And then N, 180. 15 months. Or 15 years, right? 180 months. All right, so look. So this represents that payment for those values. But with the formula, you'd have to write it this way. Okay, so then if I wanted to see that meaning, if I wanted to see those values plugged in, but then I wanted to use that in something else, like in another formula, right? Or in another function, this is going to explode, right? It's like we have to put this whole expression in for payment into something else. And so then your formula is like, it's exploding up into something really ugly and hard to read. Whereas if you just wrote this, embedded in something else, that would be concise and clean, easy. All right, any other differences or advantages to functions versus formulas? That's the big one right there. It's the compactness and like practicality of it. We can take that. It stands for that value that we can plug in and we can just substitute it in other places. But then it has the whole meaning of it, right? It has all the values right there. Yeah, Veronica.
For the function notation one, I noticed probably only had like 3 different variables, but could you use like a huge amount of different variables and it would still do that? Or is like, depending on the function, obviously, having multiple variables, but could you use function notation that way as well, or is it just 3?
Yeah, so there's no limit to how many. You're talking about having more independent variables. Yeah, you could have 4, 5, 6, depends on what you're computing. Yeah, so there's no limit to how many independent variables you could have, right? And the more that you have, probably the more complex the formula gets and the more efficient and helpful function notation would be, right? Okay, there's another advantage. So applying that is, what about if we wanted to graph? Say we wanted to, for this situation, we wanted to graph, say what the payment was at different interest rates. Is that what you did?
Yeah.
Was that the, okay?
Yeah.
So if I want to graph this for different interest rates, how would I use the formula to do that?
You would just
So I want to use the formula to graph for different interest rates. So how would I do that?
so you have like that fixed. All right, yeah, is it fixed variable? Because you just leave 175,180
Okay.
like as is, and then you turn your interest rate since it's varying into like an X, and then from there, couldn't you have like set your equation? Yeah, just input
So
those
tell me what
values.
you want. Tell me what to write, Jason.
So do like, yeah,
Y equals. Tell GC to graph, right? PMT with that graph for different interest rates. So how am I going to use? What's that? Yeah, that's just we'll graph 1 point. If I do y equals PMT, what will it graph? Nothing. And what will that graph look like? Yeah, so that the payment has a particular value right now. So if I do y equals payment, horizontal line, right? So for no matter what x is, you're just going to get the value of that payment. But what I wanted to show is for different interest rates, I want to know what the different payments are. So I want like a more kind of actual meaningful graph. Okay. She wants me to copy and paste this whole thing. I can find my cursor. There it is. Copy and paste the whole thing. And do what? Wherever there's a 0.0625, and I'll put x. Right? Versus, what's another way I could graph this function of getting the payment for different interest rates? Show me an alternate way. So tell me, what would it be? Can I copy and paste that? Okay. So here's an application of this idea of using function notation for convenience and efficiency, right? Yeah. Does it work? Does it make sense?
I don't know why you changed the X then.
So what will that do? What will GC do then? So it'll go back to the function f. So first of all, the y and the x tell GC what? On the graph. And so based on the definition of f, what will GC do on the x-axis? Based on the definition of f, what's GC going to do with the x-axis? What's that? But how is it going to, so what's it going to do with the x-axis, right? So just the x, y, putting x here does what in terms of graphing it?
Oh, it lets the rate vary.
Right, and it's going to take, it's going to, by putting x there, it's going to come here and say, so in your formula, I'm going to let x vary on the axis, and so that's going to let these r's vary. And then y will equal what? The corresponding payment for all those different rates. And then it'll plot a set of points. Okay, so a big goal of this course is that that you develop a function mentality, like about calculus and algebra. So let's continue that conversation here. Get rid of the split screen. Let's go back to this. Okay, so a distance that a motorcycle travels from an intersection in miles is a function of the time elapsed since leaving the intersection in minutes. Okay, we're going to name this relationship G, or name this, yeah. So distance a motorcycle travels from an intersection in miles, function of the time elapsed since leaving the intersection in minutes. Name this relationship G. So, if I wrote that up there, what comes to mind? What do you think when you see that? So just, what's your reaction? Don't try to tell me the right answer. When you saw that, what did you think?
Miles from the intersection after you've gone 8.3 minutes.
So when you say what is miles from the intersection? What about that is miles from the intersection?
The G, like the function of G, that's basically your dependent variable.
Okay.
So basically that's just gonna represent like the number of miles you've gone. But since we don't have like a rate or anything, we just have to say it as like 8.3 minutes after.
Okay. So what I heard you say was the G is what represents the miles from the intersection. Is that?
Well,
No, what up there, right? So what that you're looking at represents the miles.
oh yeah, the function of
So what?
So G and then parentheses.
The whole thing?
Yeah.
Okay, so he's saying the whole thing represents the miles from the intersection. You agree with that? Agree with that?
Well,
So is G, go ahead. Add 8.3 minutes. It's the distance from the intersection. Add 8.3 minutes. Okay? Is G a variable or a parameter? What's that? Neither. She says neither. You say it's a variable. What do you guys think over here? Is G a variable, parameter, neither? It's what we say?
It's the relationship.
Okay.
Okay.
So what's your answer then? Neither or variable?
Neither.
Okay. Yeah, so G is the name of the function, right? It's not, in this case, not variable or parameter. Okay? So good, all right? So that's what we want. We want to see the whole thing as the value of the dependent variable. In other words, a number of miles, right? A number of miles from the intersection. Okay? For some function whose name is G, when the value of the independent variable is 8.3, a number of minutes. Okay, and that's kind of where we landed in our discussion. That was good. Okay, any questions on that? All right, what about, so analogous function, 3f, the function f is 3x squared plus 8x minus 17. Okay, you ready? F of 2. You see f of 2. What comes to mind when you see this notation? What does it mean? What comes to mind? Veronica.
For every x in the function, you're going to put in 2.
So to do something.
Yes.
So when you saw f of 2, you thought do something. Agree? Okay. What about in the previous example? G of 8.3. Did that mean to do something? Okay, no. But now f of 2 means to do something?
We're given the function definition.
Okay. So I guess the question is, do we need to do something?
No.
Do we need to do it? No. I mean, so does it have meaning or not if we don't do it?
It still has meaning if
It still has meaning.
you don't solve for it.
And what's the meaning, Winston?
It's the relationship when x is 2 of the function named f.
It's the relationship.
It's like what that equation. It still has the meaning of what the answer is, even though you haven't solved.
Okay, and let's be more specific about the answer. So what?
The answer is that
So
equation.
The answer goes back to doing, right?
Yeah, but it still has that meaning without actually.
What?
Solving.
So what meaning?
It still means the answer of the solving without actually solving it.
Okay, but you're still relating it to doing it.
Yeah.
So can we say what does it mean without relating it to doing it? Yeah. So, yeah, the value. So the value of the dependent variable, right? It's the value of the dependent variable or the value of the function when the independent value is 2, or when x is 2, right? Okay. So that's first and foremost. So it's something apart from doing something. But so it's okay. That's how you've been trained, right? You were trained that you see that, you got this, do it, right? Like, so plug 2 in, crank it out. But that's not what this means. It means the value of the function or the value of the dependent variable when x is 2. And you don't have to do it. You don't even have to think about doing it, right? So it's still the value of the dependent variable function whose name is f, and the independent variable has a value of 2. Now, if we want that value, yes, we can do it. I think it's 11. 11? Was it? It is? 12 plus 11, I think. 12 plus 16 minus 17? Yeah, it's 11. So, sure, but the doing and the answer is all, secondary to the meaning of that, which is the value of the function or value of the dependent variable. Okay. All right, so let's look at this. Okay, so given two quantities represented by y and p, suppose that p is a function of y. Okay, if p is a function of y, then how might we use function notation to represent that? P is a function of y. P of y. Is P of y? So given two quantities represented by y and p, p is a function of y means P of y. Agree? Not a trick question. What is y and what is p if I write that p? That's p is a function of y, right? What's that?
Well, wouldn't it be the name of the function?
P would be the name of the function, right? Would it be the quantity, the varying quantity? No, right? So that doesn't work. P equals f of y. f. Is that right? Does it say p is a function of y? P and y are the changing quantities.
Well, so it's saying like P is like it's gonna have a value.
Yeah, saying, yeah, so two quantities are represented by y and p. P is a function of y, meaning p changes in a certain relationship when y changes. Or when, as p varies, y also varies in some relationship. So, choice A or choice B? Or another choice? Does B work? Yes, B works, good, okay? So it never told you the name of the function, but told you what gave you variables for the dependent, independent variable. So that would be, this would be P as a function of Y. So I used Z instead of F, capital Z. So where in this above statement do you see a function definition, dependent variable, independent variable, function name, and function notation? Go, talk. What did you guys say the function definition was?
You said it was the 3y squared plus 8y or something.
Okay, so, oh, there was another one, function rule. So, function definition, is it just the right side? It's actually the whole thing. So what's the right side? That's the rule. I didn't know there was that last one. Just the right side is what we call the rule, or like the formula part, right? So the whole thing is the function definition. Okay, what about, where do you see the dependent variable in that statement? But P is not in that statement. Z of y? Is that the dependent variable? Yes, Z of y. Z of y is the dependent variable. Independent variable? Easy. Function name? Just Z. Function notation. All right, notice, and the function rule is the right-hand side. So notice that two of these had the same answer. Which two had the same answer? Right. Going back to the meaning of function notation, right? What is the meaning of function notation? The meaning of. What's the meaning of function notation? Just say the other one. The value of the dependent variable, right? It's the value of the dependent variable. The function notation gives values of the dependent variable of a function. That's the key. Function notation represents, expresses value, a value or values, in this case values, right, of the dependent variable. Where do you see the value of P up there? What's that? So where in that above statement do you see the value of P?
But then again, we described it as it be Z of Y, wouldn't it?
No, the answer is not nowhere. Where in this statement do you see the value of P? The whole thing? That whole thing is the value of P? He wants Z of Y. Agree with that? Is that the value of P?
It could also be the function.
And could be what?
It could be the function
The rule as well, right? So it could be P is Z of Y. P is also 3y squared plus 8y minus 17. Either or, but not the whole thing, right? The whole thing is the equation, but either side, yes, either side on its own is the value of P. How about this? Is Z equals 3 a valid statement? So what, if a student wrote that, what might they be intending to write? P equals 3, maybe? What else? What about Z of Y equals 3? Is that valid? That's maybe what the intention was, right? Z of Y equals 3 or P equals 3. Yeah, so we did that. Okay, so what about 1b? Using the function name w represent the distance d at any number of seconds t. What do you say for that?
W
W of t? D equals W of t? Yes, D equals W of t. Good. Okay, so what about, tell me how to represent in 2C, the car's change in distance in the third 4-second time interval after beginning to move. How would you represent that variation in time using what we defined?
So since our third interval
Okay.
of 4-second
Yep.
time, it'd be between 8 and 12.
Good.
So you just have to find the difference between that space.
What are you going to say? W12 minus W of 8. Very good. Okay. And then how about D? So let's do 2D. Yeah. W of x plus 7 minus W of x. Is that what you guys said?
So I said X, but it should be T.
Or T.
I guess T equals X, so it doesn't matter. It would be X, actually.
Yeah, because we said so we said W of t, so it would be x. It would be x because we're letting x be the value of t here. Okay. And then what about 3D? Did you guys get to 3D? So what would 3D represent? Could you say that in words? Let's give that a shot. Distance traveled 3 seconds after h. Since the distance traveled in 3 seconds, okay. So let's think about starting time and then variation in time. So what's the starting time here? And what's the variation in time? So then let's phrase it that way. So this is what does this whole thing mean then? Want to try it? Okay, that's true. Starting at 3 seconds. How else could we say that? Instead of saying 2, 3 plus h seconds, we could say starting at 3 seconds and then. What's that?
Going
Yeah, so then for a time variation of h seconds. Right, starting at 3 seconds over a time variation of h seconds. It would be the distance, the variation in distance.